So far, we have represented a dynamic system as a box, and this box has a certain output and it has an input. And so this representation, even though it's a graphical representation, so it's easy to understand, it's not very quantitative. So we need to somehow make this attributes, this input, this output, and what this box is, we need to make this a little more quantitative so that we can use math to describe it. So let's start introducing the notation that we are going to consider in this course. So we are always going to call the output y. So the output is y, and this output y is at every time t. So there is always this variable time t. This is an omnipresent variable in a dynamic system, because a dynamic system is something that changes over time. So without time we don't have a dynamic system. So we have the output y of t. At every time t, this output, we are going to assume that we are dealing with a vector, and so we are assuming that our output y is going to be a vector of dimension p. For the input, we are going to use this notation. We are going to always call the input u, and we are assuming that the input has a dimension given by m. So the input can be a vector as well. Now, what happens inside the system? In the system, there is something that is called state, and the state is going to be represented by x of t, and we are going to assume that the state has dimension n. So summarizing, we have input u of t, that is in m, the output, that is y of t, and it has dimension p, and the state x of t at every time t is a vector with dimension n. Okay, this still doesn't tell us what's happening, how mathematically related these quantities are. So for every dynamic system, we are going to assume that there are potentially two possible representations. So for a dynamic system, we have two possible representations. For a dynamic system, we have two possible representations. The first representation, we are going to call it state space representation. State space representation, and it is a representation of this form. We are going to have a derivative with respect to time of x. So we know that the derivative of x is going to be given by a function, and this function can depend on the time t, on the state x at time t, and on the input u at time t. And the output is given by another function h that depends on t, on x, and u. Don't worry, we are going to see an example of what we mean by state space representation. But we can have also another representation. Let me introduce this alternative representation that is called input output representation. And this only involves the input and the output, not the state. So the difference between the state space representation is that there is this sort of auxiliary variable, let's call it auxiliary so far, that allows us to write this equation. So the state represents what's happening inside the box, the mechanisms inside the box, and once we have solved for the whatever happens inside the box because of the input, we know what's in the box, the state X, and this allows us to determine the output, again along with the input U. Instead, in the input-output representation, this variable X, the state, is not represented. It's a relation that is going to involve just the input and the output Y. And this relationship is in this form. We have G and we have Y, and then the derivative, the first derivative of Y, and so on, and then we can have a certain number of derivatives of Y. I'm going to call this order D K Y, and then we have U, and we have the derivative with respect to time of U, and potentially up to KU derivatives of U equal to 0. So as you can see, we're still using differential equations, but in this case we have an explicit differential equation or better, a differential equation that is explicit with respect to the derivative with respect to time of X. Instead, in this other case, we have a differential equation that does not involve the state X, it just involves the Y, U, and the derivatives of Y and the derivatives of U, and it is implicit in the sense that you don't say, as in this case, that the first derivative of X is equal to a function. In this case, they're all together, and it's not necessarily true that you can solve with respect to one of these derivatives with respect to the others. So what I'm saying is that we have a differential equation in U and Y, and of course their derivatives, that is an implicit relation. This might look a bit abstract, so let's try to see an example, and it's good, I think, to see an example that we are familiar with, so that we can understand the difference between these two representations. So what I'm proposing is to consider an example, and as an example we have already seen this in the other lecture, the RLC circuit. It might be a bit boring example, but since I assume that everybody is familiar with it, that's going to be probably the best example to understand the differences between these two representations. So let's consider an RLC circuit, and our RLC circuit is given by a voltage generator. Well, I'm not giving it a name yet. Then we are going to have a resistor. Our resistor is denoted with R. We are going to have a capacitor. The capacitor is C, and then we are going to have an inductance. So the inductor has inductance L, and this is our RLC circuit. So this is not a dynamic system yet, because remember, we have the box, and we need to know who is Y, who is U, and who is X if we are going to go for a state space representation. Otherwise, if we just have u and y, well, we just need to write a relationship between the input u and the output y, but we don't know who the input u is, and we don't know who the output y is. Well, let's choose to have as input u the voltage generated by the voltage generator. And now we have to choose. This is a natural choice after all, because that's the only thing that we can really manipulate the way we want. We can decide this generator to generate a voltage with a certain profile, I don't know, a square wave or something like that. But what we still have to decide is the output y. And for the output y, we could choose several things. We could choose the current in this circuit, or we could choose the voltage, I don't know, that is at the two ends of the resistor, or the voltage on the capacitor, or the voltage on the inductor. Let's decide. By the way, we have drawn our circuit that we go for the voltage at the two ends of the capacitor. So we decide that our voltage on C, on the capacitor C, is going to be our y. And now let's decide. Let's find one representation. It's very convenient sometimes to use a state space representation. So the state space representation, at least for RLC circuits, it's easy to get, because the only thing that we need to choose as a state is the current that we have in every mesh of the circuit, and on every inductor in the circuit. So if we choose x1 as the current, x1 is the current for L, and we have, if we choose as x2 the voltage on every capacitor, this is always going to be a good state for a passive circuit. So if we have this choice, voltage for C, on C, if we choose this, we just need to write some fundamental equations involving the capacitors and the inductors and the mesh of the circuit, and then we already have our state space representation. Indeed, if we have this, if we choose x1 and x2 in this way, we have that, at least for the relationship that we have on the capacitor, tells us that x1 is going to be equal to C, the derivative with respect to time of x2. This relationship simply tells us that if we call this current I, we have that, and we call this instead capital V, we know from the basic relationship that the current that goes through a capacitor is given by C, derivative with respect to time of the voltage applied to the capacitor. So this is one state equation. We have a second state equation. So if we go back to our state representation, we have that our y has dimension 1. So if you remember, the dimension of y is equal to p. We have called it p, so p is equal to 1. The dimension of u, that is given by m, is equal to 1. And the dimension of x instead is equal to 2, because we have one capacitor and one inductance. So according to this choice, we have that the output is a scalar, the input is a scalar, but the state is not necessarily a scalar, it can have higher dimension. In this case, it has dimension 2. And we have already written one relationship for the state that is given by this. This is a fundamental relationship for capacitors. We also have another relationship for the inductor. We know that if we take the voltage applied on our inductor is going to be given by the voltage applied on the inductor is given by L derivative with respect to time of the current of the inductor. So this is the voltage on the inductor. If we add to the voltage on the inductor also the voltage that is on the capacitor, that is X2, and if we also add the voltage that is on the resistor, that is given by Rx1, we know that this needs to be equal to the voltage that is applied by the voltage generator. So we have the second state equation. And now what we need to do is, remember, we need to put everything in this form where we have the derivative of the state on the left-hand side and the function of time, state, and input on the right-hand side, so that we have the state equation. So let's do this. If we take the derivative with respect to x1, derivative with respect to x1 of time is going to be equal to minus r divided by L x1, and then we have minus 1 divided by L x2 plus 1 divided by L u, and this is the first state equation. The second state equation is where the derivative of x2 is, so we have derivative of x2 with respect to time needs to be equal to 1 divided by c x1. So as you can see, this has the form derivative with respect to time of x equal to a function, and let's see what we have here. We have x and u, so we don't have time, but let's say in general we might have time. And to stress the fact that in this case we don't have time, I just cross it over. But this is a function of just the state at time t, not any derivatives, just the state, and u. And now we need to finish our representation in the state space, to write y as a function of time, x, and u at most. If it doesn't depend on time, even better. If it doesn't depend on u, even better. So the other equation that we have that our y is the voltage on C that happens to be x2. So we can write that y is equal to x2, and this is y as a function h. It in general can be a function of t, x, and u, but in this case we are actually quite lucky because it doesn't depend neither on t nor on u. The first equation in the state space representation is called state dynamic equation. And this is the output equation. Output state equation. So this is a way to obtain our representation immediately using this trick that works for passive circuits, where we just use as state components the currents over all the inductors and the voltages over all capacitors. So this is our state space representation. We can also obtain the input output, or any input output. It's not necessarily unique. An input output representation. How do we proceed for the input output representation? Well, it's not that we is going to be anything radically different. The only thing that we are going to do for the to obtain an input output representation is again to use exactly the same relationship, but now we are going to write this relationship without using a state x. So we are just writing them right away. So from physics, we know that if our C is given by this voltage V, we know that I is equal to C derivative with respect to time of V. So we write that I is going to be C the time derivative with respect to time of V. And then we write the other equation that we had here. We are just using I and V as physical quantities, not as states. And so we know that L time derivative of I plus Ri plus V needs to be equal to U. And now, since we know that I is given by this relationship here, we already have it, let's plug it in here. And this gives us L derivative with respect to time of I is obtained by having L, C, and the second time derivative of V plus R. We have I, so we plug it here. We have RC derivative with respect to time of V plus V equal to U. We write this better, and we write it in this way. LC, second time derivative of V plus RC time derivative of V plus V minus U equal to 0. This is our input-output representation if we replace V with Y, since after all V is our chosen output. So since Y is equal to V, we have our input-output representation. That we can write in this way. LC, derivative with respect to time, second time derivative of Y plus RC, derivative with respect to time of Y plus Y minus U equal to 0. Since we use time derivative a lot, in control theory, we have a shorthand notation. When we want to take the time derivative of a variable, for example y, instead of taking writing the time derivative, we just put a dot on top of the variable, and that means that we are taking the derivative with respect to time. If we have to differentiate twice, we put 2 dots, and if we have to differentiate more than 2 times, we can put 3 dots. Then yes, then after 3, if we are taking derivatives of an order that is higher than 3, yes, then this notation doesn't stay elegant, but at least for the first and second derivatives, it's actually quite handy. And so our state equations take this form: LC y2 dot plus RC y dot plus y minus u equal to 0. And this is how you typically see expressed an input-output relationship in when you're using in automatic control. This is a very, very common way of representing an input-output relationship.